Great. Volume okay? Great. So to finish us off on this session, I wrote this talk to be fairly conceptual, and then a lot of the concepts were covered already in some of the excellent previous talks in the statistics sessions today. But I feel like for the last talk of the day, standing in between you and dinner, it's probably not the worst thing to be kind of recapping at a high level some of the themes that have come up earlier today. So to start us off, radial velocity extraction is based on a fundamental assumption that the stellar spectrum is constant. We all know this. It doesn't matter which radial velocity extraction method you're using, template matching, forward modeling, cross-correlation function, they all fundamentally assume that you have a fixed stellar spectrum that's just moving back and forth as a Doppler shift, and that's what you're measuring. We also all know that this assumption is broken by real stars. In particular, putting surface features onto the star will break this assumption. So in this illustration, we're using Starry, made by Rodrigo Luger, to forward model of what a spectral line will look like as a star spot rotates across the surface of the star. And as you see, the line shape changes, which will induce a false radial velocity when you're measuring this with that false assumption of constant spectrum. So what can we do about this? We can and do model stellar variability like this as a coherent radial velocity signal in the time domain. But we also know that this is wrong, that the activity signal is not truly a radial velocity shift for the most part. It just shows up as one. So this can work well, but it can only take us so far. I also will note that even if we're happy with the approximation of the signal as a radial velocity shift, it does set pretty stringent requirements on the kinds of data that we take, in particular the timing of our observations, so that we can actually observe these activity signals as coherent modelable things in time. So I put in a little plug here for a paper that just hit arXiv today, led by Arvind Gupta, that calculates the limits on the information that you can get out of radial velocity time series under different assumptions about the coherent structure of stellar signals and different observing strategies. And you can also check out Chris Lamb's poster here, which applies a similar framework to the specific case of follow-up in radial velocity of transiting planets. Right, so moving beyond treating stellar activity as a radial velocity signal in a time series, we also know that we can regress the radial velocities that we measure against activity indicators in order to get a little more information on the ways in which these activity signals might manifest. So the classic cases here are things that are derived from the line shape in the spectrum, including the cross-correlation function bisector, or things that focus on specific regions of the spectrum that we believe are highly activity sensitive, like the cores of calcium H and K lines is one example. But in reality, these are just a couple more numbers that we're pulling out of the spectrum. And we actually have a lot more information than just these activity indicators and the net radial velocities at our disposal. So in this talk, I want to argue to you that in order to break through the sub-meter per second stellar signal barriers that we're currently facing in EPRV, we're going to need to make more complete use of the information in the full spectrum that we have already recorded and might as well use in our data analysis. So as one illustration of this, I want to highlight what we do know about the sun and the solar spectrum. This is plotting the two solar atlases taken with the Kit-Peak Fourier transform spectrograph in the Wallace et al. Atlas papers. One is a patch on a quiet sun, and one is the umbra of a sunspot. And you can notice that the atlases reveal the spot spectrum is different from the quiet spectrum everywhere. In the lines are changing, different lines are changing differently. And even in regions that you wouldn't necessarily select, for example, for your cross-correlation mask, there are changes happening in the spot spectrum. For many stars, the spots are cool enough that you're actually getting molecular lines starting to form that aren't in the quiet star. Basically, we expect that there's information everywhere. I pulled this as a somewhat random example of just a bit of spectrum, although if you were at the Sun as a Star workshop at CCA a couple of weeks ago, you might recognize that this is actually my new favorite manganese line. But the information is everywhere in the spectrum beyond just this little bit. So let's make use of all of it. Why not? If we expect that the spectrum that we're receiving is a combination of spectra that arise from a set of different components on the surface of the star, for example, a quiet spectrum and a spot spectrum, and the Doppler shifted version of the spot spectrum as it rotates across the star. That makes a pretty straightforward prediction that the data can be represented in a low dimensional latent space. So here I'm going to discuss one such model that I've been working on with Lily Zhao and David Hogg. And the model that I'm going to describe is designed to be very simple and very interpretable, not necessarily the best method ever to solve for stellar variability, but something that we can understand and use as a good proof of concept here. So I'll walk you through the procedure that we follow using these beautiful cartoons made by Lily. So we put some spots onto the surface of a star. And the first thing we need is data. So using Starry, again, we assume a spot spectrum and a quiet spectrum, and we forward model what the spectrum that we observe will look like at different times and different rotational phases. Now that we have the data, we want to choose some basis vectors, representations of how the stellar variability manifests in the entire spectrum. There's a few different ways that we can choose these. We can take a data-driven approach, for example, taking a subset of the data and doing PCA on it to see the dominant ways that the spectrum changes with time. Or we can construct such vectors using physical expectations, for example, using spot and quiet spectra that we have and Doppler shifting those spot spectra to create the signature of a spot rotating. No matter which basis vectors we choose, what we then want to do is project the data onto the basis vectors to find at each time of observation what the amplitude is that that vector manifests in the data, or what fraction of each basis vector is represented in the observation. So that allows us to assign for each spectrum in time a space that it occupies in the latent space or in the basis vector space. And that's what's shown here. Basically, every part of, every like place that the star can occupy within this activity space has a unique location within the basis vector projection space. And the position in that space tells us the current activity state of the star. So we can take advantage of that and do a linear regression of the radial velocities against those positions in the basis vector or the latent space. And we've done this with some toy models and find pretty good performance, both in terms of reducing the RMS of the measured radial velocities and still preserving true Keplerian signals. I do want to emphasize that although this performs well, it is a simplified model and not necessarily the best possible approach. But I think that the main point we're trying to make here is that we've shown that under the model assumptions we're making, we do have the information in the spectrum to really back out what is happening in terms of the activity state of the star and use that to correct the radial velocities in the full spectrum. So from that kind of proof of concept, where can we go from here? One way to go forward is building in more physical interpretability. And to do that, we have the flexibility to choose these basis vectors or to otherwise change our model to incorporate more what stellar spectral models predict. So Lily and I are working with Mariela Vietas on incorporating semi-empirical model predictions. I also wanted to point to somewhat related work by Khaled Al-Mula, who's going to be speaking about this tomorrow, I believe, breaking down the spectral model into different line formation temperature regions, which I think is a really promising way forward. We have plenty of room to try new statistical methodologies beyond this linear projection method. And I'll highlight that a lot of advanced techniques have been developed for the CCF that could be adapted in similar ways to work on the entire spectrum. I'll also point to Mikhail Cretinier's work with projecting the spectrum into shells and using a PCA method to break that down. And finally, just note that we want to actually build these sorts of models into the pipeline as early as possible, because proper treatment of instrumental effects and tellurics are going to be really critical if we want to have a full forward model of every pixel of the spectrum. So in the final time, just to revisit this simplified model that I gave you of the spot, when I described what was happening in the star with the spot rotating across and different emergent spectra, what I described might strike you as being very similar to Doppler imaging. And that is indeed probably where we might want to go with radial velocity modeling in the future. So what would a forward model RV friendly Doppler imaging model look like? Rodrigo Luger worked on this and has shown this really intriguing model using Starry to do Doppler imaging, putting down a spot that has a different emergent spectrum from the quiet star and going in and retrieving both the emergent spectra and the map of the star. Because if we have a brand at CCA, it's probably building models that have a ridiculous number of free parameters, but this is the proof of concept that he did to show that you can indeed, for some kinds of stars, retrieve both the emergent spectra and the map for this. So let me just leave you with some takeaways. I think that stellar spectral variability is motivating the development of new data analysis methodologies. And I would argue that for these methodologies, we want to use as much information that's encoded in the spectra that we record as possible. And I would also say that we should use the physical picture that we have of what's happening on these stars to guide our models as much as possible, even when we are using a data-driven kind of approach. And with that, I'll thank you and take questions.
Thank you, Megan. Are there any questions?
Thanks a lot, Megan. So just this spot thing, I think it doesn't come from nowhere, right? Because in '87, I think Steve Vogt did exactly the same thing, doing Doppler imaging. But otherwise, so when you try to model the full spectrum, what you will hit a wall at one point, because at the level of spectral line, you don't have enough signal to noise to extract the effect. And you can see that all the lines behave somehow differently. And so I think where we have to go is to find some lower dimension than the spectrum. The CCF is too low dimension because we average all the signal together, but to find an intermediate space where basically you don't, you correct for instrumental systematics and so on, but you still have the activity signal there. And I think it's really the way to go. We have to find this intermediate dimension space where we'll be able to really use all these techniques.
Yeah, I agree. And I think the line by line technique is a good kind of intermediate way of reducing the dimensionality for that. On the note of the spot model, yes, writing spot on the star was an homage to Steve Vogt's work. And you can check out Rodrigo's paper for more details. But in general, we're definitely not trying to fully reinvent the wheel of Doppler imaging here, but this is a forward modeling fast analytic approach that may be possible to enable full Bayesian retrievals, which has not previously been possible in Doppler imaging. So that was our contribution.
Any other questions?
So when you fit your linear model with the basis to the RV, do you make sure your bases are orthogonal to each other?
Sorry, it's a little hard to hear. When we're constructing the basis.
Yeah, do you make sure the bases are orthogonal to each other when you fit that to your
Yeah,
RV?
yeah, we do. So PCA, for example, is a way of naturally orthogonalizing the basis, but also if we're constructing it from a model, we would want to incorporate the orthogonality and require that too.
One last question.
Yeah, great talk. Maybe I missed it, but how do you extract the vectors in the latent space? Is it PCA or do you also use other things?
Yeah, we've tried a few things. So right. So one approach is to do PCA. We've also tested, I think the results that I was showing you on these slides were actually for the model-based approach, where we can construct something based on what we believe the spot spectrum will look like. But PCA was the data-driven way that we did this. And I think there's a lot of flexibility and possibilities to do other things in addition to these.
Great, let's thank Megan again.